Ladies and gentlemen, please be seated. We are about to start the first section of the forum today. So we are very pleased to have Dr. Chen-Mou Cheng from BTQ startup. Chen-Mou Cheng received his bachelor and master degree in electrical engineering from National Taiwan University in 1996 and 1998, respectively, and received his PhD in computer science from Harvard University in 2007. He then taught cryptography and information security at National Taiwan University, Osaka University, and Kanazawa University. In 2022, he joined the startup BTQ, where he currently serves as the chief cryptographer, working on developing long-term post-quantum solutions for securing blockchains. Let's welcome Dr. Cheng. This section is 30 minutes, 25 minutes talk plus 5 minutes questions. The floor is yours.
Yeah, thank you, Dr. Xie, for the nice introduction. You guys can hear me, right? Is it okay?
Yes.
That I call
yes.
up? Okay, great, thank you. Thank you again for having me today. So I will be giving a very brief high-level overview to the post-quantum cryptography. I hope that's helpful. That's going to be helpful for most of the audience here, no matter whether you're working on quantum or post-quantum crypto related work. So before we start, let's first briefly review the classical or pre-quantum cryptography. Here I'm using the ECDLP-based cryptography as an example. This is so far the most efficient public key crypto we know of, including all the post-quantum crypto. So at the end, I will compare the state of the art in post-quantum crypto against classical pre-quantum public key crypto to give you an idea what kind of challenges we are facing when we migrate to post-quantum crypto in the next few decades. So the classical public key crypto, there's a very fertile, it's a very fertile ground. So a lot of these crypto primitives are based on this problem, what we call a discrete log problem. So the general formulation is when you have a cyclic group, and then when you have a group element, let's say G, and you raise G to an unknown power X. So that just means take G times G times G times itself X times. And when you show this result, that's called the H here, and ask people to solve the exponent X, that's analogous to the logarithm function. And that problem turns out to be very difficult for a lot of groups. For groups in number theory or in elliptic curve crypto, and that motivated Diffie and Hellman to develop the very first public key crypto system, well, at least known to the public, back in 1976. So the construction is very simple. You can see that, for example, in this case, Alice and Bob wants to establish a joint secret. So Alice would send Bob G to the X, and Bob would send Alice G to the Y, and each of them know their own secret exponent. So they can simply exponentiate the ciphertext sent by their counterparty, and they will get a common secret, which is G to the X times Y. This is just a simple application of the law of exponentiation. And that turns out to be extremely useful, and we've been using it for almost at least 40 some years, until, maybe not yet, until in the back a few decades ago, Dr. Shor discovered that, well, this is all good until we have quantum computers. So Shor's algorithm, in short, I'm sure that the audience is a lot more familiar with Shor's algorithm than myself. So I won't embarrass myself with all the detail, but it suffices to say that we cannot use elliptic curve cryptography and many other classical public key cryptography, you know, in the next decades, when people are literally racing to build large quantum computers. So a lot of questions raised to answer this challenge is that, how about QKD, this quantum key distribution? Again, I'm sure that the audience is a lot more familiar with this than myself. I'll just say a few sentences how I understand, for example, a classical QKD scheme called BB84. So here, instead of exchanging numbers, exchanging some information between Alice and Bob, that so the information. So if we look at the, for example, this slide, the secret information here is hidden in the exponent, but Alice and Bob are actually sending some derivative information of that secret. So in this case, they're exchanging g to the x and g to the y, and this will be known to the general public, actually, everybody else. So this assumes that this problem, this discrete log problem, is difficult because, again, we need to assume that when somebody sees g to the x, it's very difficult to recover x from g to the x. So if we come back to QKD, in this case, there's no such computational assumption because the secret now is encoded in physics, in quantum physics. So Alice would take a photon, for example, and put it in a random, so there are two different bases. So it will kind of put the photon in a random polarization. And if Bob happens to use the same basis to measure the photon when he receives, then they get the same bit. So if you can see the in the last row, only when Alice and Bob are using the same basis for polarization and measurement, can they achieve a shared secret. And if everything is done uniformly at random, there's a roughly 1/2 of the probability that they will get a secret, shared secret that way. And they can also discuss over the public channel whether they're using the same basis or not. That's all fine. So the security here does not lie in the hardness of any computational problem, but rather it lies in quantum physics. So that's very good. That's in fact what we call an information theoretical security, because this means that no matter how strong, how fast your computer is, how much computational power you have, you cannot break it, because there's simply no information to an adversary that can help the adversary to break the scheme. So that's perfect, right? At least at the beginning, people think that this is going to revolutionize, replace all the crypto, and turns out that it's not quite yet. So, for example, QKD has this functionality of key exchange. So you can, again, establish a shared secret between Alice and Bob. And that's very useful. That's what we use every day. In fact, as we speak now, I'm using HTTPS. So I'm using that kind of a functionality, key exchange. But there's another part of the public key crypto that we don't yet have a quantum equivalence or quantum construction. which is digital signature. That's something quite different. In short, a digital signature ensures that the message indeed comes from someone who claim. It guarantees the authenticity of the origin of the message. So if I send a message with my signature attached to it, then everybody can verify that this message indeed comes from me rather than impersonator. So we don't know how to do this public verification. I mean public verification. So signing once and having everybody be able to verify many times, even into the future, like 10, 20 years from today. That's the first challenge. And even if we look at the key exchange functionality, there's also some limitation here. So for example, in QKD, because of the famous no cloning theorem, we need to physically ship the qubits from Alice to Bob, or for that matter, whenever you use some quantum crypto, you need to exchange the actual physical qubits. So this means that typically these qubits are encoded in photons or what have you, and they don't travel typically very far. So for example, it's very difficult for me to imagine that a photon can reliably travel for more than 100 kilometers. So in this case, people need trusted relays. So so you need some middleman there, and that's really that's at least a red flag when it comes to crypto, because if you can trust somebody, then you don't necessarily need crypto at all. So that motivates us, I mean, post-quantum cryptographers, to look into alternative schemes that whose security is based on computational hard problems. Again, just like the classical one, but they have a different set of assumptions. So, namely, they don't rely on this discrete log problem, or a close relative to it is integer factorization problem. So we're looking into alternative mathematical problems that may be hard for quantum computers to break. So we don't know yet. So it seems today, according to my understanding, that quantum computers cannot really solve, for example, all the problems in MP, right? So therefore, it's very likely that there are some problems that both quantum computers and classical computers cannot solve efficiently. So therefore, after decades of research, today we are looking at roughly five different families of crypto that are believed to be quantum safe, meaning that basically, to be honest, this just means that we don't know how to break them with even with a large quantum computer. But maybe tomorrow there will be another Shor or some smart guy comes and break one of them. I mean, it's always like this. In crypto, we try our best to break we try our best to break a crypto system, and if it can withstand all these attacks over, say, many decades, then it's likely that they are secure. So I will briefly tell you what these post-quantum cryptography crypto systems are about. So the first one is hash-based signature. So this was actually pretty old, almost like the classical one, like the classical Diffie-Hellman. So it was first proposed by Merkle in late 1970s. We will give an example later. And the second family is code-based encryptions. This is also quite old. So first presented by McLeish in 1978, and it's believed to be also secure against the quantum computer's attack. And the security assumption here is it seems quite difficult if you have so the decoding problem in encoding theory, when you don't have a good structure or when you hide the structure of a code, it seems very difficult. So that's the basis for the security there. And then there are other 3 more younger branches. So multivariate cryptography, pioneered by Matsumoto and Imai first in 1988. There, the assumption is the difficulty that we don't know how to solve multivariate polynomials efficiently in general. So as long as you have a quadratic equation, you have a set of quadratic multivariate equation over some finite field, then the best algorithm we know how to solve this tend to be exponential. And we don't know how quantum computers can help. Finally, another hot kind of popular method to obtain post-quantum crypto is lattice-based crypto, first proposed by Attile in 1996, which I'll give some more example later. And last but not least, there's a new family called isogeny-based crypto, first proposed by Defao, Zhao, and Plood in PQ Crypto when I organized PQ Crypto 2011, more than 10 years ago in Taipei. They proposed this hard problem. So it's some problem on elliptic curves, but not the discrete log problem. It's about some special kind of functions between elliptic curves. And they got into NIST competition, so which I will also describe later. But unfortunately, recently they got broken. So if you're following all this news, you will see that some people say that isogeny-based crypto is dead. But in fact, I want to stress that it's only one instance, so one possible construction in isogeny-based crypto, and this branch is still alive, and there's a lot of research going on. So that's a quick summary of the 5 main families of post-quantum crypto that we know of today. So maybe there will be more. A lot of smart people are working on this. They come up with new and innovative ideas every day. So maybe we'll even see more in the years to come. So now I want to switch gear to talk about standardization. So it all started in PQ Crypto 16 in Fukuoka. So you can see these are the people, a group photo taken in that conference. In this NIST competition, which I will talk about in more detail later, but we selected so far 2 families, 2 out of the 5 families, 4 algorithms to standardize. I mean, by we, I mean NIST and the PQC community. The first one is hash-based one-time signature. So the standardized version is actually multi-time, but I will start by explaining the basic idea behind this hash-based signature. So as I told you, Lamport discovered this quite early, more than 40 years ago, and the idea is really simple. So assuming we have a hash function, so you can think of it as a one-way function. So it's very difficult when I show you h of something to recover that something. So you just think of them as going one way. We can have a signature like this. So basically, we can have a private key, and we can hash them. They will become the public key. And depending on whether you want to sign a 0 or 1, you can reveal that private key. For example, if you want to sign 0, you just show me S0, and anybody can check whether h of S0 equals to P0, which is the public key you published earlier. And then you can generalize this to sign a multi-bit message. But you can only sign it once, because once you reveal, every signature reveals part of the private key. And there are ways to organize a lot of these, many such one-time signature key pairs into a Merkle tree, which I will not go into detail today. And we can also make this signature, this Merkle tree stateless. So remember, so when we put all these one-time signature key pairs into a Merkle tree, and each of them still can be used only once, right? So we have to remember which key pairs we have used. But then there's a trick of building a really, really big tree, so big that the probability of reusing is negligible. So this is the earliest idea, is usually attributed to Goldratt back in 1987. But at the end, the result is that we can have a stateless signature, just like all these other signatures. And the best thing about hash-based signature scheme is that there's no additional computational assumption other than that we need to have a secure hash function. So hash function being a secure hash function being one that's very difficult to invert, which is pretty much required everywhere. So if we don't have this hash function, then we don't have crypto almost. So that's really a minimum assumption. So now another family is this lattice-based crypto. So a lattice is a discrete subset in an n-dimensional Euclidean space. And since it's discrete, you can imagine that problems happen. Problems in a lattice tend to be difficult than problems in the Euclidean space itself, because every time when you, for example, integer programming tends to be very difficult. But if you relax and you allow all the coefficients to take on over all the real numbers, then it becomes linear algebra, which is easy. So here, a difficult problem is that to find a short non-zero vector in a lattice, in a Euclidean lattice. So when the dimension n is, say, a few thousand, this problem seems very difficult. And we can build two variants based on this SVP, this shortest vector problem. So the left one, the one on the left is called learning with error. So here we're kind of we have a secret S here, and then we kind of show you some samples of this S. So we have some random matrix A, and each row kind of represent a sample of the secret S by taking the inner product. But every time it's not a perfect sample, it's a noisy sample. So it's a sample with some error. And the surprising fact is that no matter how many samples you take, this problem seems to be hard. So simply because there's an error in every sample. And alternatively, we can also kind of rotate the matrix, and we can look at the problem of short integer solution. So here we're looking in the kernel of the matrix A. Since A is A has more columns than row, then the kernel space is non-trivial. There are a lot of vectors here. So finding one integer solution is very easy. It's just linear algebra. But finding a short one, a short enough integer solution, seems also difficult for the same reason that when we move to linear programming to integer program, things suddenly become so much more difficult. So with that, I will summarize the NIST PQC standardization. So I will give you an update on that effort. So first, in PQ Crypto 2016, NIST announced that their intention to standardize post-quantum crypto. The requirement is that the algorithm must run on classical non-quantum computers, and but they have a very wide spectrum of applications. So they want algorithms to run on very constrained devices, to those like on the internet, like servers, and also scenarios including in some cases they want the algorithm that can survive in a very limited with very limited communication bandwidth. So in earlier this year, they decided to standardize 4 algorithms. So here are the 4 algorithms you can see. So 3 of them belong to the lattice-based crypto. That's why we spend some time introducing what the underlying hard problems, the security assumption is. And the final one is, the last one, Sphinx, is based on hash. And they're going to open another round next year. So the due date is July. So they probably want more diversity. So probably anything that's not lattice nor hash based. So in the last minute, I want to talk about some problems. So here's a very quick summary of the sizes that this new algorithm, along with ECC, the good old classical public key ECC, so the sizes of these algorithms. So we can see that in terms of public key and ciphertext, if you say add these two together, these post-quantum algorithms tend to have much larger public key plus ciphertext. So with the only exception of Sphinx, so where the public key is the Merkle root, so it's only 1 hash value, it's very small. But on the other hand, the signature itself is very, very big. Not to mention that the signing process takes extremely long time. So we at the BTQ, so I promise this is the last slide. So we at BTQ, we are addressing this challenge. So we have a signature aggregation technique for Falcon, and potentially generalizable to other lattice-based signature schemes, which we call PQ scale. So the idea here is that we don't need to keep all these signatures, because they are there only to attest that these messages are authentic. They come from a signer, an authentic signer, so to speak. So we apply zero-knowledge proof technique here. Then we can say, remove all these signatures and still be able to prove or to show that all these transactions are valid. So as a result, we can get a compression ratio of about 27 times when we aggregate, say, around 4,000 signatures. So in general, the more we aggregate, the better compression ratio we can achieve. So if you're interested in this technology, so please feel free to contact us. Okay, so I guess I'm running out of my time. So thank you very much. I'll be happy to take any questions or comments.
Okay, thank you for the nice talk. Do we have any questions from the audience? Also, if you have questions from the online audience, you could just type in your question into the chat box, and we would read it out. Okay, maybe I would ask one. So in the next final list, which one do you have? Do you believe it's more secure than the rest? So for example, the lattice space, there are a few of them. Do you have any common of those algorithms?
Yeah, that's I guess that's the $1 million question, you know, Dr. Xie. So if you ask me, of course, you know, kind of I guess most people would agree that Sphinx plus, so the one here I'm showing at the bottom row, is the most secure, simply because that it assumes the least. So the only security assumption is that we have a secure hash function, which is also necessary in all other crypto schemes, including ECC, including Kyber, the Lithium, Falcon, all these other algorithms. So the assumption used there is a subset of the assumptions used in other algorithms. So for the other 3 NIST you know, algorithm that NIST is going to standardize, so Kyber, Dilithium, and Falcon, in addition to a secure hash function, they also assume some hard problems. So some problems are hard to solve in Euclidean. Some problems involving Euclidean lattices are hard, even when we have large quantum computers, which, you know, as of today seems to be true. because no one has come up with a quantum algorithm that can solve these problems, this short integer solution or learning with error problem on quantum computer. But maybe an expert like yourself, Dr. Shea, and your colleagues, I actually encourage you to look into this problem, and perhaps you can come up with a much clever, better algorithms. Then that can help the crypto community as well, because we need to know how hard these problems are in reality, as opposed to just assuming that they're hard without actually checking it.
Thank you very much. Thank you for the very nice explanations. Okay, I think it's about time to end this session. So let's thank the speaker again.
Thank you very much.
Thank you.
Thank you for having me.